Hello and welcome back. Let's finish up by looking at some limits of piecewise functions. So here we've got a function is going to be a piecewise function with three different sections. So for this function we've got the absolute value of x when x is less than 2. Function is going to be 2 when x is between 2 and 3, and our function will be 4 minus x when x is greater than or equal to 3. So for x is less than 2, so everything from 2 to the left, we're going to have the absolute value of x. So between 0 and 2, we're just going to have a nice straight line. This is because the absolute value of a positive number is just itself, and this is just a line y is equal to x. F of x is equal to x. When we start to look at negative numbers, the negative number will become a positive number. So for instance, at negative 1, the absolute value of negative 1 is 1, the absolute value of negative 2 is 2, so we just get this line right here, if I could draw a straight line. So this should just be a v. But we have an open circle here because this function, this part of the function only extends up to 2, but not including 2. So we have to look at the next part. So between the values for x, 2 and 3, where the function height is going to be 2. Well, here's 2, so the function height is going to be exactly the same along here's a horizontal line, and it extends from 2 all the way to 3. So we have an open dot at 3 because the function height isn't 2 at 3. And then the last part, we've got 4 minus x for x is greater than or equal to 3. So the slope is going to be negative 1, so it's going to be going down and to the right. And the y-intercept is going to be is going to be 4. So here's the y-intercept, and if we go, and if we're going 1 down and 1 over, our function is going to start here and then continue like this. So again, this includes x equal to 3, so I've got a closed stop there. So let's do a few limits here. We have the limit as x approaches 2 from the left. So here, let's mark this off. So here is where x is going to be equal to 2, and as we approach 2 from the left, we follow our function up, and we're going to hit our wall here right at 2. So this limit, as we approach 2 from the left, will just be 2. As we approach 2 from the right, so again, here's 2. As we approach from the right-hand side, we see that we hit the same place. It's just going to be right at 2. So this limit, the full limit, exists and is just equal to 2, since the limit from the left and from the right are the same. So let's get rid of a few of these lines. And now let's look at as we approach 3 from the left and from the right. So again, here is where x is equal to 3, and as we approach x equals 3 from the left, we're following our function along, and we see that we're also going to hit this wall at 2 exactly. So from the left, f of x, the limit is going to be 2. From the right, as we come from the right to where x is equal to 3, we're going to be down a little bit. We're going to be down here at 1. So the limit from the right is going to be 1, which means that since these limits aren't the same, we can't talk about the limit, the whole limit. This is simply not going to exist. And again, we think about the limit as x approaches 3. This means from both the left and right simultaneously. So clearly, if we approach from the left and the right, we're approaching at 2 different places. Our lines don't meet, so there is no limit. It can't be both 2 and 3 at the same time. Now, not for some functions, they won't tell us the exact equations that govern the function, but they'll just give us a picture of what it is. So we've got a couple of limits over here. We've got the limit as x approaches infinity and as x approaches negative infinity. So again, as x approaches infinity, what we mean is as we go further and further to the right. as x gets bigger and bigger and bigger, what's happening to our function? Well, our function is just kind of going up, and with this arrow, we're somehow indicating that we're just going to keep going up forever. Well, if we go up forever, that means that our function is going off to infinity as well. So as x is going to infinity, the function height is also going off to infinity. Okay? We also have the limit as x approaches negative infinity. This means as we're going to the left. So what will this be? So as we go further and further to the left, as x gets more and more negative, we're at this height down here, and we're never changing. We're just flat, and we're continuing along. So this function is just going to be -2 forever. So we've got a couple of functions as we go as we go to the left and to the right. Let's look at the function. Let's look at the limit as x approaches -2. And again, this isn't from the left or from the right, so we have to consider both the left and the right at the same time. So as we approach -2, what's going on? Well, as we approach from the left, we're approaching this open circle, and as we're approaching from the right, we can see that we have the same limit from the left and the right hand side. So as we approach from the left and the right hand side, our function height is always at -2. So the limit exists, and it is -2 since as we approach, we're approaching at the same level. Now, the maybe slightly tricky thing is that what is the function directly at -2? Well, if we come over to here to -2, we have an open circle down here, but the closed circle's up there. So if I plug -2 into this function, I get 2. So it's kind of nice to notice that the limit as x approaches a of f of x, doesn't always have to be equal to f of a. So if I just plug in a into my function, in this case -2, I get a different value than what happens if I approach a from the left and right. So this is just something to keep in the back of your mind. We can't just plug in a value. We have to think about it a little bit more. And then the last one here, what happens is x approaches 3, and again, there's no plus or negative sign here, so we're just going to consider what happens as we approach 3. So as we approach 3, let's say from the left, we're going to follow this curved line, and we can see that we're just getting closer and closer to 0 here. So from the left, if we think about the left-hand side, we should be getting closer and closer to 0. So let's record that for the moment. If we're coming from the right-hand side, we're also traveling down, and we're also going to crash into this right at 0 as well. So the function height as we approach 3 from the right-hand side is also 0. So even though we've got this sort of this like the kink in the line, we've got this cusp going on, the limit exists and it's equal to 0. So again, one way to sort of picture this is if your lines are coming in and they're going to hit at different places, no limit exists. Limit from the left and limit from the right exists, but not overall. Even if they're coming in at different angles, as long as they hit at the same place, the limit exists and we're good to go. So let's do one final example. And here we have a piecewise function. We've got fx is equal to x plus c when x is less than 2, and x squared minus 1 when x is greater than 2. So the question is, what value of c would make this limit exist? Well, when we are drawing our function, this isn't a very good axis, but anyway, over here at 2, our function is going to be doing something to the right hand, on the right hand side. It's going to look like this function. Who knows what that function looks like? It's going to be wiggling around. Over here we've got x plus c, so we don't know exactly what this is going to look like. So maybe it's doing something like this. If c is one value, or maybe if c is another value. We want to find the exact value of c so that these guys match up. Why is matching up important? Because then the limit from the left-hand side and the limit from the right-hand side are going to be the same. So what we want to do is make this so that the left-hand side and the right-hand side match up. So let's think about what the limit is as we approach 2 from the right-hand side. So let's draw a little bit more accurately. So we've got out here at 2, we're going to look like x squared minus 1. Well, x squared minus 1 is going to be a parabola. Maybe I need to make this look a little bit nicer. So x squared minus 1 is going to look like a parabola. It's going to look something like this. And our function only looks like this when x is greater than or equal to 2. So we want the part that starts at x is equal to 2. So if we erase that a little bit, when x is equal to 2, x squared minus 1, so that'll be at 3. And we're going to continue on with this little parabola. So it's going to sort of curve up a little bit. Cool. So as we approach 2, as we approach x is equal to 2, from the right-hand side, we're just going to hit 3 exactly. So the limit as x approaches 2 from the right-hand side of f of x is going to be 3. If we follow this parabola down, we're going to get closer and closer to 3. Now comes the left-hand side. So the question is, what does x plus c look like? Well, it's got slope 1, and the y-intercept is going to be c. So for instance, if c was 0, we would have slope 1, and we'll look something like this. So the y-intercept would be 0, and we'll have slope 1, and we can kind of see that they don't match. So the question is, what value of c should we plug in to make this straight line with slope 1 end up at 3 when x is equal to 2? So again, we have x plus c when x is equal to 2 should be 3, because we want this to match up right there. So if I plug a 2 into x plus c, I should get 3. And that means that c should be 1. So we can check this as well. So now, if we were to think that we should plug in a 1 in for c here, what would this look like? Well, the y-intercept would be 1, and we'll have a slope of 1. And as we approach 2, our function is getting closer and closer to 3, which is good. So the limit as x approaches 2 from the left-hand side of f of x is also 3 when c is equal to 1. So if we want this limit to exist, we just have to have the same approach from the left and the right-hand side, and we see that that happens when c is equal to 1. When c is equal to 1, both of those limits from the left and the right are exactly equal to 3.